So the entire thing
Is
was based
ironic.
in a premise of.
Please stop.
Sorry, math hasn't even started yet at 12:30, which is funny when people give slips like that. The whole not play was a premise of satire. So like we're gonna put on a play that tells you why not be in a play. So Ava's monologue was even more irony. I'm too shy to be in a play. Let me give a 3 to 4 minute. It was longer than 2 minutes. You were talking for a good minute. That was a lot.
She reported for the little like people. Like I was really surprised.
I only got a $350 scholarship though.
What did you get for Shallow?
375.
That's so good.
Yeah, that's pretty sweet. All right. Today's lesson is going to be real fast. If you don't have one of each of these sheets, please come grab them. Sorry they weren't in the back, but 7th grade has
Should we
sheets
do
today.
a rough
So.
draft or should we use page for
Either for the first one, but we may actually just skip this.
Oh, okay.
So you can be approximate as long as you're using all straight lines. Like your drawing can be approximate.
I'm gonna get a ruler. Can you get me one?
Yeah.
Okay, that is a weird one. I opened this, and it looked. I imagined that they slide. Are you working on this or on the paper?
We'll be working on those. What are we on today? 8, 2, 1. Alright, so it says a little thing. The only reason I want to talk about 821, I mean, a lot of this is going to be reviewed from Math 1. Why? Why that? So think with your partner or on your own, how can we prove or show or whatever we want to say the sum of those interior angles, and how does that statement matter? Sorry, man. Not with high fives.
What? That's what I know.
Let's not find so you know. Oh, yeah, I'm going like right. No. That's good.
Why would that information be helpful? Why would that little reminder, how could that come into play? Ava? So I can draw some, what do we call lines that we add into...
Line. No, there's a word. I forget what it is, but I know what you're talking about. Where you draw the lines. It's to help you. No. It's nothing that we've been doing recently. It's a word. It's
Yeah. That.
What did you say?
Auxiliary.
Auxiliary lines. Add some auxiliary lines to your drawing. And we're going to be doing a lot with auxiliary lines today.
Yeah.
So I have this angle, and this angle that I'll call my red triangle. I have this angle, and this angle, and this angle that I'll call my blue triangle, and then sure, for fun, let's say green triangle. This angle, and oh, yeah.
It's still here.
So, wait, how many sides did this shape start with?
5.
5. How many triangles did we make?
5.
3. What do we know about each triangle? Let's start to use some hands. What do we know about these, Chris?
Each triangle has a sum of 180 degrees.
Okay, Ethan, how's that help me here?
You can just like add up all the triangles' degrees.
Yeah, if I know that regardless of what size each angle is, these 3 together make 180. Those 3 together make 180. Those 3 together make 180. So while I could like fight for a little while trying to figure out what red plus green is, who cares? If all these are 180, all those are 180, and I need to use all of them, right? All of these are at my vertexes. There's no angles here that don't get used. So if I add them all up, what would we get for our angle sum?
540.
Yeah.
So let's use this to make an argument, right? We're going to try to make some kind of mathematical rule or something that we can use many times over. So on your resource page with your partner or on your own, if that's what you've chosen, investigate, and if you remember the rule, good for you, but let's investigate why this does happen, why the rule's allowed to be used, and how you could justify it to somebody else if you were trying to like represent how we find the interior sum of a 100 gon, right? Or an any gon, really is what we're talking about. So take a couple minutes. You might get to the point where you remember the rule from Math 1.
I don't.
I know the rule, but I don't know the rule. I know.
We also just, hey, we can fill this in. Right, we just said, well, we had a 5 gon, right? And it was 540. So pentagon, but they won't all have nice names.
Oh wait, Ricky, practice for every.
Dude, I have extra pencils. I'm here to support you, as opposed to leaving my class. You like ask for help, maybe. Septagon.
Oh, I was gonna say heptagon.
Heptagon is maybe, it might have two different names.
Does it matter how we split up the triangles?
You tell me.
I don't think so.
Well, then it'd have to be really specific.
I really don't like it.
Now Ava.
But also in that case, it doesn't matter.
Okay, so you asked, does it matter how we split up?
It does, because if you split it up like that, actually, wait, no, you can say
So I could, even though that line looks wrong, as long as I don't make any points here, don't make any vertexes there, I could split there, but that's still not a triangle. So split there again. Now I've made triangles. So it doesn't matter as long as we're making triangles. Okay? Rule for this.
I think I might. This might be like coming back from Math 1. I don't know.
Okay.
But I don't know how to like exactly word it out. But what you can see is that each time you can treat like 3 if you're doing a recursive or exponential as like the first term, and like 4 is the second, 5 is the third. And 1, which is not how they're doing it. They're doing it as like n equals 3, third term, n equals 4.
Okay.
So it could be 100, or not 180. I need to know my base value. Never mind. But I was saying, like, if I'm doing this, it would be like 180 times the n term minus.
Wait, I know.
Now hold on. So I like what you just said. Owen is shifting his perspective, and he's saying this is the first term in my sequence. Its value is 180. The second term in my sequence is 360. The third term is 540. However, that doesn't quite work with the ends that they gave us. This could be looked at as recursive. So add 180 to the previous value. Or if we try to write it explicitly, Owen then ended up saying, I'm going to take my 180 and I can't multiply it by n, but I can multiply it by n minus 2 to turn this term number, or this n, into that term that we want.
Yay! I did it right. Sorry. I have
And that's
a
our
hard time
rule.
with
The interior sum of any, doesn't need to be regular, doesn't need anything special, is 180 degrees times n minus 2. Now you tell this to somebody and they don't believe you. Like, nope, no way. No possible chance that it's that easy. I feel like, well, I mean, it is. But how do you get them to believe it? How does what we've drawn up here...
You plug it in.
Oh, okay, sure. But when you plug it back into something that you already know, you're just proving what you already know.
You use the angles.
You plug it in so that
and you count the
What
number.
do you mean plug it? I mean, what, like...
Plug in the n term for, okay, let's just say, look, if you have someone here, and they're already, like,
So think about proofwriting, right? I'm just going to pause you for a second. Think if you had to define statement, reason, like, think about that stuff. How would we justify that all we're doing is 180 times n minus 2? Yeah?
Well, if you just count the number of triangles, then you know
The
that
auxiliary line.
How? So how do we know how many triangles we're going to get, though?
you subtract 2 from the number of sides.
Why is it that?
Because it is. Wait, it's like, if you're drawing one line, then it has to share sideways.
Auxiliary lines. Are we even talking about this? I mean,
Wait,
honestly, like what you were discussing.
Auxiliary lines have to be drawn from an angle to another angle, so they automatically use up like 2 sides.
Auxiliary lines have to be drawn from vertex to vertex that are not adjacent. Right? So adjacent vertex to vertex, that would just be your edge, and that's not an auxiliary line. That's what we already have. So here, there are 2 vertices unloved. They get left out of the equation, right? Here, well, we got Valentine's Day coming up, right? Here, 2 vertices left out of the equation. Here, 2 vertices left out. Because we're always creating triangles, and the first triangle that you create, like when you start making triangles, has to skip a vertice, and the last triangle we create has to skip a vertice. We know that in any polygon, creating the maximum number of triangles will be 2 less than the number of vertices. Which the number of vertices is also always your number of sides. Chris?
So I have a question. How do you prove that a circle is 360 degrees?
That's beyond what we're like.
Hi. That's what we were talking about.
And that's not, so we're talking about the sum of interior angles. A circle doesn't have interior angles.
A circle is its own.
Okay? And it's not a polygon, so it's also like totally separate from what we're doing. We're talking about polygons right now, right? Circle is not a polygon. Alright, so make sure you have this rule down. Any interior angle sum for a closed polygon will be 180 times n minus 2. So, what about 100 gone? What do we do to solve that, Colin?
That's going to be 180 times 100 minus 140 times 98, which is going to get us an interior angle sum of 17,640 degrees.
Yeah.
Oh, this is way too fast. 17,640.
Yep.
Wait,
So then for n, it's just the equation. 180 times n minus 2. Degrees. Any questions? We're going to look fast today. But we're going to do some stuff that we haven't done with this yet. So, regular, we're just going to redefine some vocabulary, make sure that we're good with this. Can anyone tell me what 2 things in a regular polygon is?
because all the sides are the same length and all the angles are the same.
How do we say that mathematically?
Both sides are congruent, and all angles are congruent.
Colin, do you have another way to say it? especially my summer math one. I was literally just reviewing and cleaning up my summer math one. What means same? Yeah, but another word for same, or prefix for same in math. Right, equa, how do you say it? Equiangular and equilateral. So, they're both, right? Equiangular, equal sides. So, regular, everything is the same. So, Jeremy says, well, if I want to find that interior angle, I can just divide. And of course, because he's in middle school, he doesn't really explain himself. So his friend asks, like, what do you mean just divide? How do we find this interior? So, for a single angle, could we write a rule? Now, this will only hold true in a regular polygon. Okay, so make sure that you pay attention. This rule is for regulars. Sure.
Okay. So basically, all the exterior angles have to equal 360 degrees. Am I right?
Well, you're not quite saying it right.
I mean, all the exterior. Yeah.
Exterior
And then
angle from an auxiliary line.
from a vertex, they all have to equal 3. They have to sum up to 360, which means that the inside has to be. Well, not complementary. Not complementary. Supplementary to the measure, the angle measure.
So wait, here's what I was groaning at. You said all the exterior angles have to be 3. Do you mean each angle is 360, or they all together add up to
I said
360?
they sum to 360.
With what, all of them together? So if I take that exterior and this exterior.
Yes, they're all the same.
Oh, so they're all congruent, but I don't think they all sum to 360. I think there's an I like where you're going. You're on a right path, but you're a little too far for us. And if you could stop helicoptering, I think that would help us focus.
I think
Yes, I mean good.
Ethan?
We could do well, first you have to like find the sum of all the angles. So that would be the like 180 and then n minus 2, and then you could just divide that by n.
I do that.
If you are trying to calculate a single, you writing this down, guys? A single angle in a regular polygon, all you need to know is what's your n.
Oh,
And
yeah.
quickly, you can just calculate the total angles and divide by how many angles you have. Or, sorry, the total of the angles, and then divide by how many you have. Now, yeah, hang on to it for just a second. We could write this as 180n minus 360. Yes, of course, if I distribute, that works. Bless you.
Thank you.
But we like to do this better. All right, Ava, you sounded like you had some.
Does gone mean line?
Gone is any, like, it's for polygon. The poly means many.
Yeah, many sided.
Yeah, so like a 9 gone, 9 sides.
So when gone, what does that mean?
Not like, I'm not sure.
So
It's
is
the
this
end of. I mean, gone is something to do with shape. Like, because poly means many, and gone is like, a polygon is a shape with many sides.
so since
I'm not 100% sure.
gone means side.
Maybe. Do some research if you want.
So then could you call a line a gone?
I really don't
Thinking
think so.
that with Ava Chapter.
So, I think this is what Jenny was trying to get us to think about. And this is why I wanted you to hang on to it for a second. So, Jeremy's like, alright, fine, well and good. But what about the exterior angles? And he's got a friend like Jenny who says, like, well, I mean, draw some lines.
There's only one to draw a line.
What?
But what if you are?
Like-
What if you're in the math textbooks?
Oh, that was in a calculator question.
I forgot about that.
So, Jenny said something pretty useful. about the relationship that has to exist. We're working with regular polygons right here. So regular, we said, all of them are equal. Like they tell us this is regular. So we know all our interior angles are equal. And then Jenny told us a relationship. But you kind of said it a couple different ways, so let's make sure we clean it up. What relationship does an interior angle have with its corresponding exterior angle? Supplementary, right? And if we can find out what that interior angle is, then we can find the exterior angle pretty easily. So then what's the sum of the exterior angles? So take a minute, first find one exterior angle, and then find your sum. Do you have the work written down for the problems we're actually doing? You are trying to find the sum of the measures of the exterior angles. But to get there, yes, you need to find A first. What is the sum of the interiors? 640. 640? $180 times 6 minus 2. Right? Is that right? So then, if that's the sum of the interiors, 180 times 4. Are we good now? I'm like, if you guys tell me we're good, I'm moving on. I'm not. Okay, we're good? Because some people had said we were good at 640. How do we then calculate one of them? Divide by 6, right?
Yes.
Because there are 6 sides here. So 720 divided by 6 is 120. Which means angle A is 60, which means, well, okay, how many of them are there? 6.
3. Oh, see, I was right. I saw all the exterior angles add up to 360.
But your wording was really, really weird.
No, I just said all the exterior angles of the polygon sum up to 360.
Now hold up. This worked once. Don't
It
get all
works
excited
every
yet.
time. I know this because
Are
I
you
did it.
sure?
I tested it on a million times. It works true.
It does work on the million.
Now why, then, if we try this with an equilateral triangle or a regular decagon or a regular octagon or a regular dodecagon, 12 sides dodec, I'm not sure exactly why we went there. Does that always work? You guys said you tried it with a million gon?
Yeah.
Yeah.
Because now we can algebraically re-represent what we're doing, right? What we did, we could write with all variables. We found the total, 180 times n minus 2. We then divided it by our n. What did we then do? Subtracted that from 180. And then multiplied that whole thing times n, right?
That's pretty cool.
Ooh, numbers.
So many numbers. You probably should write it down.
All right, so Jenny's hypothesizing.
So
What?
that's state-
Okay, she's stating with confidence.
So that's
I love
stating
it.
that, so that's stating that the sum of the exterior
It's
angles
right,
will equal
for the
360
triangle
degrees
work.
every time.
I'm testing any shape, right? I'm not just testing.
test the
Test.
head. Sweet shoot.
We're gonna do Snapchat.
No, wait.
You're my
So, hey, work through this algebra with me. Forget about the specific shapes. Let's just work this.
Regular polygon.
Hold on. This is for any, right? That, like, well, okay, so this part would have to be regular because we're assuming all the angles are the same. But even if all the angles aren't the same, then some will compensate for the others, and we'll pull up Desmos here in a second and look at that. And we distribute here, as we said earlier. This could actually be rewritten as 180 minus 180n minus 360 all over n times n, right? What would happen next?
Wait, what? I'm missing something. Why is there 360?
There's 180 times 2.
Oh.
I would do inside the inner parentheses, right? That division by n.
So that'd be 180 minus 360 over n.
So 180 minus, well, 180n divided by n is 180 minus the 360 over n. Well, that's going to stay 360 over n. Hmm?
Okay, wouldn't that be 180n minus 180n minus 60?
Because the n times divided by n.
So the division splits, right? So when I divide, I'm dividing each thing in the numerator by the denominator. This division gave me 180, right? 180n divided by n. This division with the negative gives me just, I just kept it because I don't know what n is, right? You with me there? Then I can't multiply by the index. I still have parentheses inside of parentheses. And I could, but I'd have to do it by everything. So distribute that negative, and we get 180 minus 180 plus
So just 360. Oh, we proved it. I just realized.
proof.
Whoa.
180 minus 180 cancels out.
I'm gonna write it last.
360 over n times n. This just makes 360. I put an exclamation point, but then that wouldn't be mathematically correct.
Because that would be.
That would be
very
correct.
Five times
Well,
four
that-
times 3 times
that
2
is
times
an
1.
explanation point.
Yeah. There's like, I know,
What?
but there's
It's like-
So guys, earlier when Jenny made that statement, I could have, like, if we hadn't had some background knowledge on this, I probably could have asked, like, now do you think this will hold true for every situation? And I at least, as an individual not that adept with geometry, would probably say, well, there's no way that in every shape, no matter what the size is, that this would hold true. Why? Why does this happen? Chris? Okay, well, okay, polygon's bigger than 3 sides. Because to be a polygon, it has to be closed, straight lines.
I think that's human error.
I bet you're just having an issue with the fact that your calculator can't comprehend it. Because this will work for any situation, like any. So even a 1 quadrillion or whatever, your calculator's just having issues with that then. As I just want to have myself while I walk over here. As our polygon gets larger, what happens to those exterior angles?
Do they decrease because there's more of them?
So if you check out our exterior angles here, all obtuse, right? Because all my angles inside have to be acute.
And they get more acute.
Then they get more acute. And actually, if I pull this up and I say it's not regular, and I can make one of my angles here obtuse, notice how yellow and red kind of change together. If I try to keep green the same size, as one exterior angle gets smaller, the other exterior angle will get bigger.
But they have to balance them.
They have to balance. And if red doesn't change, say I drag this way and I try to keep red the same, what two are changing?
C and D.
Yeah, yellow and green. So always two angles are going to change together, and they do complementary or like kind of inverse. If one gets bigger, the other gets smaller.
So this is
And this holds true no matter how big of a polygon.
Can I change every single angle at once? Wait, is that possible?
You can't. No, you can only drag one point on here. I mean, unless you're dilating the shape, you can set it to let you dilate. So you can play with these if you want to go in and look at that. But aside from that, that's essentially the lesson that I wanted to cover today. So I told you guys it was going to be quick and easy. You got like 10 minutes to work on your homework. Biggest things, which is ironic because this was what I was prepping today just for other work that I'm working on, is we covered this in Math 1. You go in chapter 14, which was the last chapter, we talk about polygon angle sum theorem. That is what this is. This is the polygon angle sum theorem. So we talked about all this stuff.
We did chapter 14. Yeah, we did.